Linux is a fifth.
Yeah,
Okay,
it's on the top of the screen. Okay, okay, thanks. So we were starting with protocol messages, and we are now in the middle of defining messages. So.
Yeah. So actually, maybe David, do you want to give us a little? Since we missed the beginning of the recording, and you were the smartest one who thought to record it, do you want to give us a little summary of like those 3 equations under definition 2.1, or what goes into a message? Oh, maybe we lost him. That's okay.
So should I repeat at least that we cover the base messages? So each message contains estimator value, validator name, and justification. Justification is a set of the same messages. So in the first case, the first message will be with the empty set of justifications. Justifications will be empty set. So each other message will have also the estimate value, which is calculated from justification from the previous messages. Again, validator name and the set of justifications. I'm not completely sure how this definition. How should describe this definition? Can anyone explain this?
Which one?
This one.
Yeah, so let's see. I think that script M is like maybe the set of all valid messages. So he takes the limit as n goes to infinity, and it's a set of all of the. Oh yeah, right. So he's saying it's like the union of every possible mi. So I think big M is like all possible messages
from all validators. As you said, the maximum number of messages and justifications is the number of validators.
Yeah, right. So yeah, go ahead.
I'm just wondering that justification is really just a set of messages, not a set of messages, or but no.
I think it's just a set of messages. Yeah.
But this P is a power set of sets, so this implies that this is like a set of set.
Okay, that's a good point.
But not in one round, probably. If
what
we are, if we are. If all the validators trying to make a census of one set of messages, this is like one level. It's only one set.
Yeah, I wonder if that P means. So yeah, he says below that script P is the power set, but now denote. Okay, so let's see. It maps a set to the set of all of its subsets. Right, that's what the power set is. So E of, yeah, that thing that we were talking about above denotes all sets of protocol messages. Oh, right. But remember, this is MN is like, he's trying to represent all of the messages at height n. So he's saying like you can choose an item out of that first set, which is 0 or 1. You choose an item out of that second set, the set of all validators, and then you choose an item out of that power set. So like when you write a message, your estimate isn't the set of 0 and 1. It's just a 0 or a 1. So you choose one of the 0 or 1. And it isn't a set of all validators. It's a specific validator. And it isn't the whole power set. It's one of the subsets from the power set.
Oh, I see.
That's so kind of weird definition.
So this is only a set. It's not a set of sets.
Yeah, the justification is a set. Yeah, I think that's right.
Okay, this makes sense. So yeah, now he defines the estimator function, which is really in this case of binary consensus, it's really, as you said, choosing the from all the existing messages that the validator receives, he chooses the value from the possible values.
Yeah.
With the union of empty set.
Yeah, I think it's funky to say empty. I was sort of thinking that is like nil or undefined or whatever, but I think that so the estimator in this case can return one of three things, right? It can return 0 or 1 or nil. And I think it basically always returns 0 or 1, but there's a couple special cases. Oh, in fact, he says them in that sentence right afterwards. So it can return nil if you don't have any justifications yet. Like if you're just starting the game and you haven't seen any other messages, then the estimator, it can't estimate, so it returns nil. And then the other case where it returns nil is when the score, when it's a tied vote, when like half the weight has voted for 0 and half the weight has voted for 1.
You mean in this case?
Yeah, let's see. It's hard to see. It says,
Oops.
It's okay. I can see it. I just had to hold it up. So a protocol message M is said to be valid if either the estimate of the if the estimator returned nil, or if the estimate actually matches what the estimator said it should be. That's the second case.
Oh, this one.
Yeah, right. So remember the estimator, that script E is the estimator. It's a function, and you give it a bunch of messages and it gives you back an estimate. So the way Vlad's writing this is he says the messages that you pass into that estimator are all those messages from the justification. So you've gathered together all these messages you're going to use as a justification. You run it through your estimator. In the second case, the one you have highlighted right now, the estimator like actually gave you an answer, 0 or 1. So for your block to be valid, the estimate that you include in your message has to be whatever the estimator said. And then the other case, sort of the edge case, is when the estimator gives you back nil, which means either you don't have any justifications or you had a tied vote.
Oh, which is the case when you can choose whatever you want.
Yeah, bingo.
Because, yeah, okay, yeah, that makes sense. Cool. So here he defines like a function for extracting the estimate value from the message.
Yeah.
It's just the first item from a tuple.
Yeah, exactly.
And in the same way, I think this is the V function for extracting sender and J for extracting justifications.
Yeah. So maybe we should practice with some of this notation. Like if we write out a message, let's write out a message. So we know it needs 3 things, right? So then we can practice like what's E of M, what's J of M. You want to do that?
Maybe I can, yeah. Do you see my screen?
Yeah.
What were you thinking, that we can write example of messages, or?
Yeah, so we know a message needs 3 things, right? He said M is something from the set 0, 1, something from the set of validators, and something from this power set of all these other messages we've seen. So like, let's just write out an example message. Yeah, we'll write one right here. Perfect. Yeah, nice.
So we can say, okay, it's 0. We can say
Yeah.
this is a sender, and justification is like an empty set.
Yeah, good. Yeah, that makes sense. Okay, so cool. So he defined those helper messages. So let's see, like, David, do you want to take a stab at telling us what like E of M0 is? Or do we still have him on the call? Maybe not. Yeah.
Yeah, I'm still in. Yeah, sorry. Go over that again, please. Go over the question again.
The question is, so Tomislav wrote out, yeah, so here's the general form, right? A message has an estimate, a validator, and a justification. And then, so like, here's an example of one. This M0 is 0, Alice, and an empty list. So then my question was, like, just to help understand the notation, what would E of M0 be in this case?
What would E of M?
Yeah. So we're gonna try to come up with E of M0 equals, and then someone can tell us the answer.
Okay, I don't have an idea yet.
So we are constructing message M0, and message 0 contains 3 values. And the first value is like the estimate value that this message is saying that I want to choose this value for consensus. And the second thing is the name of the validator who create this message. And on the third part is all the other messages that this validator have received.
And just so I can, sorry to interrupt, but the reason why you only put in the brackets is because, and again, I could totally be wrong on this, only because we're assuming that Alice just joined because there's nothing to justify with that.
Yeah, Alice didn't receive any message before.
Bingo. That's exactly right, Jeremy. So this is like, it's like the beginning of the game. She hasn't heard any other messages so far, so she that list is empty for her.
All right.
Okay. So I'll do this example.
Yeah.
Oh yeah. Go ahead. Yeah. Go ahead.
The estimate could be 0 or 1, right?
Yeah, we can write that like all possible values are 0 or 1.
Oh, okay.
Mm-hmm.
Because we are in a binary consensus game.
Okay, I get that.
So we can create another message, for example, from Bob. So when Bob received a message from Alice, he will create a new message, and he will execute his estimator function. So it's not E, it's like a special sign E. I'm not sure how to.
Yeah. Yeah, perfect.
So I will choose like a Haskell notation. It's because the input parameter is a justification, right?
Yeah. So this is the. I'm not too sure. Yeah, just show us what you're thinking, and then we can figure out what the notation means.
So here is like a function name, and here the like one parameter.
Okay.
And the result is also 0 or 1. And for Bob's case, this will be the J will be M0. And because he sees Alice with a 0, he must answer 0 for his estimate. So for E of Bob, when he executes this function, this will be 0.
Okay.
So he will answer. Yep.
Sorry to interrupt. So now I just want to like take what you just said a step further, right? And ask this question. So let's just say, hypothetically speaking, maybe I should probably hear you explain it fully before I even ask this question, but let's just say Bob came in before Alice. He already got the justification from the other nodes around them that they're all starting to vote 1. But Bob is malicious, and so Bob changed it from a 1 to a 0. So when Alex joins and then tried to justify her results based off of Bob's, what does that then do to the binary? Does that offset it? That's one of the questions that I have in terms of that. Where how can that 1 in a million chance? How can you guarantee that whoever is newly joining, who doesn't know what's going on, just trust the node beside them? Is it going to be malicious law to offset any potential binaries?
So the critical thing is what Bob cannot say here. I'm saying it is 1 because he's seen Alice's message, and if Bob says this is 1, all the other validators, when he sent his messages to other validators, all the other validators will know immediately he's lying, because in his justification, when he create his message, so this is validator name, and in justification he will put message from Alice. So when Bob sends his message M1 to the next validator, the next validator can easily execute some kind of verification function, or I'm not sure is there some kind of name for this process, but he will immediately know that this estimate value is correct with these justifications. And I think that to answering your question, Bob can, if Bob didn't see any other messages, and later he finds out that here in the smallest group of I want to say that other validators can be in majority and change the value of his own opinion, and he will put all these justification messages in his message and say, okay, because of this other majority that I received now, I must change my opinion to the correct value. Does this make sense?
Yeah, it totally does. Thank you for clarifying that for me.
Oh, no problem. Please interrupt me for every question.
All right. So far in this game, we've got Alice sent the first message, and she just arbitrarily chose 0. And then Bob saw that message, and he, evaluated his estimator. He passed in the message he had seen, and it said, Bob, you should also estimate 0, because the only votes he had seen so far were for 0. And so then Bob sends a message where he also estimates 0. It's from Bob. And now his list is no longer empty. Like, Alice went first, so her list was empty. But Bob has actually seen Alice's message, so he included that in his list of justification there. Right?
Yeah.
So, I'm curious, do you think, I don't know how hard this would be. I wonder if it would be possible to show these, the notation we're using today is like Vlad's notation, right? And in the past we've used this game diagram. I wonder if we could show it in both ways. I don't know how hard it would be to do both.
Yeah, we can try that. So we can say, for example, Alice, he says 0. I will not show weights because everyone can have a weight 1 and right.
Yeah, yeah. Do it however they can all be 1 or whatever. Yeah.
So here we have Bob. Yeah, L is constructing the zero value. Okay, we can say here. Oh, we can say it like this. And empty set.
Yeah.
And Bob says 0, name, and okay, message from Alice, which is, maybe we can write it like this, M0.
Oh, nice. Yeah.
Oops. Okay. So we can now have, we must have another validator.
Yeah, to make it interesting.
So let's say this is from, and this will include, what we want, to have all these messages included, or?
If this block includes both of the existing messages, then they'll instantly come to consensus and we won't see anything too interesting.
Yeah, we can have like another.
Maybe Claire has a slow internet connection and so she hasn't seen those messages yet. And she starts out by guessing 1.
Oh. And Claire says 1. So now we can have, okay, this is like Claire with 1. And she also have like a empty set.
Yeah, I think this is a really good idea because the way on the right makes the game more visual and like kind of easy to understand by looking at it, and then the math notation is what's hard though, and so we're doing both of them. So I wonder maybe we can draw in another like graphically draw in another block and then see, I don't know if someone wants to come up with the like notation for it. Oh, it can't be called M0 though. That one that Claire sent, we've got to call that something different.
Yeah, this is M2. Yeah, and then this is like really the number of messages that are coming to validators.
Yeah.
So the Claire will send his message to Alice and to Bob.
Yeah.
Right. This is also possible. And for example, if Claire sent a message to Bob, what will Bob do? Because Bob already sent already created this message and sent to some other validator? Can we have another validator?
We can make a fourth one if you want to.
So we can have like if we have only 3 with 1 weight, it will be undecided. Well, really not, but. What will be the fourth?
David, I guess.
Yeah, nice.
And David will have only message from Claire.
Yeah.
And he will decide 1. But David can also receive a message from some other validator, but.
So yeah, someone can create a second block now.
And he will send his block to, but he will let's say that he will receive this later. And how will, it's difficult to represent that David sent the message to Bob.
Yeah, we haven't so far represented like who a validator sends a message to, because the funny thing is like, so let's say David only sends this message to Bob, but Bob can still forward it along, like Alice can still receive it because Bob's job is to gossip those along to everybody else too.
But we are saying that Claire didn't receive message from anyone?
Not yet, not when she created M2.
Yeah.
Yeah. So let's have Alice create her second block now. And let's say Alice has seen, I don't know, David's block, but not Bob's maybe or something.
But this is like Alice sending second message, right?
Yeah,
here.
second message, that's right.
And she will send this message to whom, for example?
Well, these diagrams don't really have any way of showing who the message was sent to. They only have a way of showing who has received the message.
But isn't the problem when do you receive the message? It's like a critical or not?
Yeah, I guess I was saying like let's just say Alice has received David's message, but she has not received Bob's message. Because the thing is, we don't have any way to know where messages have been sent. Like we don't know whether Alice tried to send a message to Bob or to David. All we know is what people acknowledge having received. So like, you know, maybe here I am, Tomislav, trying to send messages to you, and I'm sending them and sending them and sending them. And then like from Jeremy's perspective, he has no idea that I've been sending you messages. All he knows is whether you've acknowledged seeing those messages or not. Because you could, you know, maybe my messages are getting lost on the internet, or maybe you're receiving them but pretending you haven't. So we don't really know whether you've received them. We only know whether you've admitted that you've received them.
And you're admitting if you sent this message in your justification.
You admit that you've received messages based on what's in your justification. There's no way in the protocol to communicate like, hey, I sent this message to Tomislav. If he's not admitting it, he's a liar or something like that. There's no such concept.
Oh yeah. But you're saying that you received message from someone else. And
yeah.
You're saying he definitely sent a message.
What was that?
You can prove that someone sent this message.
Yeah, correct. So like David can prove that Claire sent M2 because he's received it and used it in his justification. Maybe Bob also received M2, but he just didn't like it, and so he didn't acknowledge it.
Yeah, but if he didn't include this message is his justification, and someone else received message from Claire, is it possible that that someone can prove that Bob was hiding this message. Although,
no, we can't.
yeah,
So that's what they call a non-attributable fault. Like, it's possible that Bob just got that message and threw it in the trash or whatever, but it's also possible that it just got lost traveling across the internet. So we don't really have any way to know, so we can't blame Bob for it.
okay. The only case is like an equivocation when Bob sends two different messages with different justifications when it become obvious that yeah, he's received a message but he didn't send it.
Yeah, right. So okay, so let's do this. Let's do it with Alice block. What has Alice seen so far? It's up to us. You know, we're just kind of acting as Alice now.
Alice can receive. So the Bob can receive message from David.
Okay.
In the next step. And now what Bob can do and should do.
If it's only like this, then Bob is equivocating because he has not acknowledged his own previous message.
But Bob now have created his own message from justification from Alice, and now he is receiving message from David. So he's still okay. But
in order for this message that we're working on right now to be valid, it has to include in its justification Bob's previous message.
You mean who?
So there's a circle near the bottom that doesn't have a label yet, right? That's the block that we're working on.
Yeah, this is like a Bob after receiving message from David.
Right. So if the arrows are done and we write in M4 equals 1 Bob M2, then yeah.
And he will have M1.
It has to. Okay. Now it's valid. That's what I was saying. It has to have M1 in there in order to be valid.
And he will say, "Okay, I'm changing my mind, and this is okay."
But so the problem right now is that what you've written in the text, M4 equals, does not correspond to what we've drawn with the picture. The picture shows that the justification should just be M3, but the text says that the justification is M1 and M2.
Oh, I'm sorry. I mean M3. Oh, I'm sorry. Yep.
Okay, so now we're getting closer, but we're still missing one arrow. The arrow from M1 to M4.
But this is really not an arrow. This is the same validator, just in different time, a little later.
Yeah. So we need to agree on what the arrows mean. Maybe what are we thinking the arrows mean?
Yeah. Is this like gossiping and just sending message to, or?
Previously, we've used the arrows to indicate justification. So the arrows mean the exact same thing as the list of M1, M3.
Oh, I see.
Or that's what we've done previously. We can invent new notation here too to just show like where they were sent or whatever. Yeah. So now they sync up. Now they say the same thing. Sorry about that.
Oh, okay. Yeah. The arrows are really justifications.
Yeah. Bingo.
Yeah, that makes sense.
Yeah. So Jeremy, do you want to create a block, or David?
Yeah, that'll be fine.
Cool. All right. Describe one for us, and Tomislav can draw it.
Okay, so yeah, but why doesn't Alice and Claire has justifications?
Because we're assuming that they just joined. That's why they don't have anything to justify.
Oh, okay.
And yeah, so and also we're on the impression that Claire, like you say, or same thing that Josh just said was doesn't have a or a good internet connection, so she doesn't know what's going on in the network. So, all right, let's drop our own block. So let's do. Are we gonna just create a new slide, or we're just gonna just use this?
Just add one on here. This game is still progressing, right? They haven't reached consensus. So who sends the next message?
All right, I think. Let me look at this.
There isn't one correct answer here. You have lots of freedom.
Okay. So let's just say Bob sends a message. Let's create. So I guess if we create a new block, we have to redo starting at M1, or we can just do like a M5.
Exactly.
All right, so let's just call this Tom.
Yeah, but we have 4 validators.
Yeah. Validator set is complete. No new validators.
Oh, no new validators?
Yeah.
So they're really they're gossiping, and they want to what they want to achieve. Each of these validators knows how many validators exist. So Bob, when Bob received these 2 justifications, he knows from justification that he received a message from David, from Claire, and also from Alice.
Yeah, so Bob is the only
one. I'm thinking that now Bob has just messages from all validators.
Mm-hmm.
So let's have Claire create a new block.
Okay.
So Jeremy, Claire's going to create a new block here. It's up to you. There isn't like a right answer here, but you just make up an answer. Like, what blocks has Claire seen so far?
All right, Claire's seen David and Alice.
Okay, cool.
David and Alice. This is here.
Mm-hmm.
Come on. And she must include M2.
M3 as well.
M3.
So Jeremy, you said that she's seen David's block and Alice's block, right? So M3 is David's block, and M0 is Alice's block.
So
so that will be 1, because if you already. But here's the curious part, because if David is going off of Claire, so that means they already reached a consensus on that, because they all already agreed on the new block that it's going to be 1. So technically for the next block, so she wants to justify it to a new node, which is, let's just say M6, and we can call this like Steve or something like that.
Validator set's complete. Validator set's complete. No, we can't just arbitrarily add new validators, right? We're saying this game 4 validators.
Okay. But is this like a strange that David sending messages to Claire, because he received messages from Claire and now sending back? Does this make sense?
Yeah, totally. The concept of sending messages to a person doesn't really exist. When you send a message, your intention is for it to go to every other validator, everyone in the network. Now, maybe you don't have a direct connection to all of those, so like you have to rely on it being gossiped a little bit, just because otherwise no one has the bandwidth. But you don't send a message. Like, the only time when you send messages specifically to another validator is when you're trying to collude and like undermine the network.
Mm. Oh yeah. Now Claire has also like a signature from David that he's signed a message.
Yeah, right. And so like this block that we just created is still valuable because yes, even though Claire and David had both estimated 1 before, Claire didn't know that before. She didn't realize that David had estimated 1, but now she has realized that.
Okay.
And then from the Bob's perspective, he now knows that he now knows that that most of the validators have concluded 1, because he decided to have a 1 because of his justifications, and in his justifications, all the other 2/3 of like a majority of validators decided to be 1.
Yeah, right.
Is this true?
Yeah, that's true. Yeah, correct.
So now Claire can send a message to Bob, but it will not change the.
Claire can send a message, but she doesn't send it to Bob. She just sends it, and it's intended for everyone. And then maybe Bob receives it, and maybe he doesn't.
Yeah, I mean, when Bob later receive Claire's message as justification, why not write this?
Yeah, you can draw it.
Now Bob will have all the messages with M5.
Yeah, so the way that it's drawn right now, Bob has equivocated because Bob sent M6 and Bob also sent M4, but M4 is, yeah, there we go. So now we can add M4 to the justification list.
And everything is fine.
The diagram doesn't match the text right now because if you look at that most recent block, M6, the picture says that the justifications are M4 and M5. Yeah, now we're talking. Now everything's fine.
Ah, okay, yeah.
Yeah.
Because he include previous message. Yeah.
Yeah, right. Yeah, right. So M6 does include M1, but it does it in a recursive way, right? It does it because M6 includes M4 and M4 includes M1.
Now, stupid question. And this is when it goes back to the paper that we were looking at earlier. Is this what you would define as like part of the subset? So even though we brought out M5, the subset would technically be M2, M3?
Yeah, right. So we said, so yeah, that's not a stupid question at all. That's a really good question. So like, yeah, let's look at M5 for a second as our example. So we said every message has 3 pieces. It has an estimate. That's the one. Oh, sorry, I'm a little bit above that. Yeah, oh yeah, thanks, perfect. So M5 has an estimate, in this case it's 1. It has a sender, in this case it's Claire. And it has a justification, which is a subset of all of these messages. So the full set of all messages is M0, M1, M2, M3, M4, M5, M6. But the subset that is the justification for M5, that's just M2 and M3.
All right, cool. Because I just tried to visualize it, but like now that we wrote it out and I can see it, it totally makes sense now. Cool. Thanks for clarifying that one for me.
Yeah, good work. Good work.
And also, Josh, this helped me to see that this is not when we're talking about blockchain. This is not the set of sets, because you only have here the hash.
Yeah, exactly.
So you don't have to have everything. You can find it if you want, but you don't have it. You don't need to have it in your message.
Exactly right. Yeah, because it's not like these messages get bigger and bigger and bigger. It doesn't actually include the full text of M4. It just includes the literal characters M4, and then you can go back and try to look up M4. Or if you haven't seen it, ask another validator, like, hey, have you ever seen M4, for example?
Yeah, and this is like difficult to see when you have 0 and 1, and you don't have like any cryptography. Yep.
Yeah.
And we concluded that 1 pretty much overrode everything, or overrides the consensus for this.
Yeah. So here, Bob can conclude the consensus. We can.
Wait a second. Is that? I don't think that's true yet. I don't think that's safe yet, because David has only sent that 1 block so far, and if David's next block includes M0, M1, M2, M3, then he could switch his estimate to 0, because that would be a tied vote, right?
But, but David already sent his message with this justification. He cannot send different message with different justifications. It will be equivocating.
If David's next message includes as its justification M2 and M1, which, oh, sorry, no, I said that wrong. I'm sorry. If David's next message includes M3 and M1, you know, and therefore recursively includes M2 and M0, then David could estimate 0 on that next block because it was a tied vote.
Can you say again? Well, if,
yeah. You want to just draw it in?
Mm-hmm. Yeah, please.
So David has a new message, and its justification is M3 and M1.
Can we write it when this happened? Somewhere. Oops.
All the way at the bottom. Oh, whoops. Oh, yeah. Okay, you got it.
All the way down after.
Yeah.
Okay.
Yeah. And David has seen messages M3 and M1. Those are the justification here.
So this is like M7.
Yeah.
So he knows M3.
And M1. Yep. And that's it. So we can draw those arrows in.
Directly from here.
Yeah. And so what that means is that David, like, even though Bob has created new blocks, David has not received those new blocks yet. He only has received that old block from Bob. Right, okay. So I think everything we've drawn is valid, but what I'm claiming is that it's also valid if M7 estimates 0.
Because he thinks, yeah, before Bob changed his mind, he receives Bob's message.
Yeah.
And he knows, yeah, this is like a 0.
Yeah. And so that's why I think that M4 that's colored green right now, there's not actual safety right there because it's still possible for David to change his mind like we just showed.
But David can change his mind, but he cannot change the final value. Or
so, sure, because now Claire can see M7 and M5 and Claire will change her mind. And now 3 validators are voting 0.
Can you say again? So Claire, you mean somewhere here? Claire can.
I can't see your mouse pointer. I'm sorry.
Oh, sorry.
Yeah, like the very bottom right corner. Claire makes a new block, M8. Yeah. And its justification is M5, M7.
M5,
Yeah.
and M7, and so from M5 and M7, what is the result of?
Well, you guys tell me. I think I have an idea, but I don't want to bias you.
Claire knows it's 1.
Well, Claire has seen her own vote of 1. There's a justification from M7 still missing, an arrow missing.
Yeah.
So she has her own vote in M5. She voted 1. But in M7, David voted 0. In M1, Bob voted 0. And in M0, Alice voted 0. So it's now 3 validators are voting 0. The only one who still thinks it's 1 is Bob.
Yeah, that makes sense.
So I don't think Bob was actually safe on M4, although he was certainly close.
Yeah. Maybe you can see in the paper what is the like a.
Yeah. That's a good idea.
Okay. Because this is here is the formula how to score and calculate this. Okay. So here's the dependency. Yeah, I'm not completely clear about this. What does it mean to have dependency of the messages?
Yeah, okay, great question. So dependency is a really similar concept to justification. Justification, we saw, is only like the direct parents, the ones that you've directly cited as justifications. But dependency, that's the recursive one. That's the justifications and the justifications of the justifications and the justifications of the justifications of the justifications.
And is this imply some kind of order of messages? Or?
It implies a partial order, not a total order.
Okay.
So he says, so let's see. He says M1 wait a second. I don't remember. We define the dependencies of a message M as all the messages M prime such that, M prime is a dependency of M. So that equation in definition 2.2, it says M1 is a dependency of M2 if and only if M1 is the same thing as M2, so that's not the interesting case. Or there exists some M prime that's in the justification of M2, and M1 is a dependency of M prime. So that notation is pretty damn confusing, but I think I can explain it better if we look at the diagram again.
Back to the picture.
Let me share.
Okay, so let's start with a super easy case. M7 is a dependency of M7. That's easy. Every message is a dependency of itself. So that's not like the super interesting case. So then we say, so let me ask you this question. Is M5 a dependency of M5?
Yes.
Yeah, that's the easy one,
Because,
right? Every message is a dependency of itself. Okay, so here's a little bit harder question. Is M3 a dependency of M5?
No, because it is not in justification, so justification of M5.
No, it is. It is. M3 is in the justification of M5.
Well, it's a no because M3's justification came from an unjustified validator, right?
So dependency means we can say, so like here's a good way to think of it. Imagine you receive M5 and you want to ask yourself like, okay, is M5 a valid block? Was it computed correctly? You can't answer that question until you know what's in block M3. Because you need to know how David voted in block M3, what his estimate was.
So the dependency mean that this is like a parent.
Yeah.
They have the same
correct.
parent.
I'm trying to avoid the word parent because parent is used in a different way when we start talking about actual blockchain consensus instead of binary consensus. But yeah, that's exactly right. Like M3 is in the justification of M5, so it's a dependency of M5. Okay, so let's do a few more, and then we'll get to the very end of that equation was the most interesting part. So okay, so let's see, David, are you still on here? Maybe not. So all right, Jeremy, I've got one for you. Is M4 a dependency of M6? And so the way you can answer that is like
no. Well, M6 has M4 as a dependency, so yes.
Yeah, exactly. M4 is in the justification of M6, so M4 is a dependency of M6. That's right. Okay, let's do another one. Is M7 a dependency of M8?
No.
It is for the same reason.
Wait. I keep looking. I keep looking at the dependencies inside M7. All right. Can we
Yeah.
do
Oh,
one
yeah,
more?
yeah. Right. The of wording. Yeah. So M7
Yeah.
is the dependency of M8. That's correct. Okay. So let's try another one here. Is M0 a dependency of M5?
No.
You're right. It is not. That's correct. Okay. So the ways that something can be a dependency are if it's the block itself. So M5 is a dependency of M5. That's not that exciting. The second way is if it's in the justification. So M3 is a dependency of M5. And then the third way, and the most interesting way, is the recursive one, where it's in the justification of the justification, or arbitrarily deep. So like, is M0 a dependency of M8? Well, M0 is not in the justification of M8, but if we follow those links back, we can go from M8 to M7, M7 to M1, M1 to M0. So M0 is a dependency of M8. So, okay.
That's some like Inception stuff.
What was that?
Oh, it's like that's some like Inception shit.
Yeah, exactly. Yeah. Inception shit is the common way to say recursion. Yeah.
And really, these arrows showing you the dependency.
Exactly. Yeah. So another way to say it is like if you can get from block A to block B by following the arrows, then A is a dependency of B. Yeah. So okay, I don't know if that was helpful or not, but I think
that made sense. That
Okay.
totally made sense.
Cool.
Yeah, this really makes sense for that. It's if it is in justification of all the whole justification chain.
Yeah. Right. Exactly. So cool. All right. Should we keep going or should we call it?
Oh, I didn't see the time, so.
Yeah.
So maybe we can leave something for the other time.
Yeah.
I think now is now we can say something about the equivocation and how it's defined and how the score is calculated. And
Yeah, so we've talked about score a bunch already, although we haven't used the word score. Score just means counting up all the votes.
all the weights, right?
Oh, yeah, the weight. Yeah, that's right. You're right. The weights. Yeah. And then equivocation. Yeah, so maybe we should talk about equivocation. Equation 5 is about equivocation. So two messages, M1 and M2, represent an equivocation, if and only if. So first of all, what does V of M1 equals V of M2 mean?
We're extracting the validator name. So the names of the validator must be the same.
Yeah, correct. So they have to be sent by the same person. So there's an equivocation if both messages are sent by the same person and M1 does not depend on M2 and M2 does not depend on M1.
Which means in our graph that for example,
I think M5. So, oh wait, never mind. M5 will be a bad one.
Claire can send or.
So we don't have any equivocations in the graph right now, but if you delete any one of those vertical arrows, then we'll have an equivocation. Not that one won't do. It has to be the vertical one that goes like from the same validator. Yeah, bingo.
And
if we delete that
if
arrow,
you delete that,
Yeah. So now tell me which two messages represent an equivocation.
This is definitely.
Yeah.
Well,
M6 and M4 are an equivocation now because M6 does not depend on M4 and M4. Oh, yeah. You're right. You got to update that. And M4 does not depend on M6.
You mean like this?
Yeah. So now Bob has equivocated with M4 and M6.
But someone else must receive this message and.
Yeah, no one else can prove it yet because no one has received actually either one of those messages. But once they do, then they can prove it. That's a good point. Yeah.
Yeah, maybe we can like a bit more specific about equivocation next time.
Yeah, that sounds good. All right, cool. It would be fun to write up some exercises where it like shows a game and it says spot the equivocation in this game.
Yeah, that would be cool.
I'm thinking of lots of good exercises actually. We could have one where we draw the graph of the game and then we say write out all of the M0 equals M2 equals, or vice versa, where we give you a big list of what M0 and M1 and M2 is and we say draw out the graph and spot any equivocations or something. Yeah.
I was thinking about actually that could totally be doable because I was thinking about using the recording after this, maybe just like write up a quick blog, just give a high level oversight of it so people can understand at least like some of what we just went over in layman's terms, because this is like really cool to know in terms of understanding binary consensus.
Yeah, Casper's freaking cool, and we can do like real number consensus, or I was thinking about come to consensus over a list at some point. So there's lots of cool stuff we can do.
Call it restaurant consensus or something like that.
Yeah. Or that would even be a great story problem. Like, Joshy, Tomislav, Jeremy, and Valentine are going to go to dinner together, and they have to agree where, and then they're going to play Casper to figure out where they're going to go to dinner.
Yeah, that would be cool.
So, all right. Well,
and who is equivocating pays the dinner.
Yeah. That's right. All right. Thank you for hosting today, Tomislav. You did a great job.
Oh, thank you. Thank you all.
All right. Bye, everybody.
See you next time. Bye-bye.
Oh, Tomislav, can you post a screenshot of this graph onto the Discord?
Oh yeah, sure.
Cool.
Sure.
Then like Bill or Jake or Isaac or whoever, Rita, can look at it.
Yeah, sure.
All right. Bye, guys.
Bye-bye.